So the last time that I saw you guys, what we did were alternating series, the alternating series test. Right, and you guys don't have to write this down because you would have this in your notes already. I'm just trying to do a recap from 2 weeks ago. All right, so for the alternating series test, so 3 things have to happen. First of all, the series has to be alternating, which seems sort of straightforward, but that has to be true. In order to use the alternating series test, you have to have an alternating series. So you would have like a -1 to the nth or a -1 to the n plus 1 in there, and that would cause it to alternate. And then 2 other things have to happen. So the series is alternating. The limit as n goes to infinity of a sub n has to go to 0. So the limit to infinity is going to go to 0. And then a sub n plus 1 is less than or equal to a sub n, which means that the terms are decreasing. They keep getting smaller and smaller and smaller. So the n plus 1th term, like the next one in line, is going to be smaller than the one you had before. So they keep on getting smaller and smaller and smaller. So they're decreasing, which makes sense that the limit would also go to 0. Now, here is the thing. The series can still converge even if this is not true. Now, this has to be true. That limit as n goes to infinity, that still has to go to 0. If that does not go to 0, then it's going to diverge. That's the nth term test. So if that doesn't go to 0, it's going to diverge. But if this isn't true, it can still converge. You just can't use the alternating series test to prove it. This test just won't work. Okay. So that's the alternating series test. And then the other thing that we looked at was the error bound. So your error is less than or equal to a sub n plus 1, the nth term. So what this means is, like, for example, if you are going to estimate the sum of the series, and the sum is adding up an infinite number of numbers in the list, you're adding up an infinite number of terms. So say you wanted to estimate it by just summing up like the first 7 terms. Say you're going to do S7. Like, I'm just going to add up the first 7 instead of like infinity. All right. So for that, the error is less than or equal to the 8th term. So if you add together the first 7 terms, that's not going to be the true answer. You only added up 7 instead of an infinite number, but the error is going to be smaller than the next term. And because the terms keep on getting smaller and smaller and smaller because they're decreasing, the more terms you add up, the smaller your error is, so the better your estimation. Okay, so let's just do one example here, and then I'll do the I'll go over the homework. All right, so say this is your series, n from 1 to infinity. It is alternating due to this -1 to the n plus 1. That's going to cause it to go positive, negative, positive, negative. So it is alternating. So series is alternating. And so we're going to do limit as n goes to infinity of 1 over square root of n. A sub n is just the part without the alternating bit. Or you can put, absolute values around this if that makes you feel happier, but you don't need to include that. So it's just this part of it. And that will go to 0. As n gets bigger and bigger and bigger, this denominator is infinitely large. So you end up with something like 1 trillionth, which is really, really close to 0. All right, and then we need to show that this is true. So a sub n plus 1, that's going to be 1 over square root of n plus 1. And it's like we just substituted n plus 1 in place of n. And that's going to be smaller than 1 over square root of n, which is a sub n. So we're showing this is smaller than this, because this denominator will be bigger than this one. this is a smaller fraction. It's kind of like a fourth is smaller than a third. Like this one has the bigger denominator, so it's the smaller fraction. For n bigger than 1. And since all these things are true, since it's alternating, since this limit goes to 0, and since this is smaller than this, the series converges by the alternating series test. All right, so that is a recap of what we did before break, and I'm going to go over the homework. So if you want to open that in another tab, or get out whatever you were writing on to do the homework, I'm going to go over these for you. Oops, too many pieces of paper. All right, so for this first one, I'm trying to zoom in a bit more here. Which of the following series converge? So we're going to have to look at each of these individually and see which ones converge. So for Roman numeral 1, this is 1 over n squared. So that is a p series where p equals 2. And again, if you have that series recap open, that's going to recap everything that we've done so far. So this is a p series with p equals 2, and so that one converges. For p series, it's going to converge if p is bigger than 1. If p is less than or equal to 1, then it will diverge, which is actually what's going to happen right here. This is a p series where p equals 1. This is n to the first. That's also the harmonic series. So that one's going to diverge. And then for Roman numerals 3, this one is alternating. So because we have that -1 to the n there. So we're going to do the alternating series test. So limit as n goes to infinity, 1 over square root of n. Actually, this is really similar to the one I just made up for us to go over. That's going to go to 0. And the n plus 1th term is going to be less than the nth term. So that is also going to converge. So the question was, which of the following series converge? Well, we got 1 and 3. And so that one is D. All right, and then this is really similar, but it says which of the following series diverge. So be really careful. This one says which of the following converge. This one says which of the following diverge. So just be careful with what it's asking you here. All right, Roman numeral 1. We're going to need to do the integral test for this one. So it's going to be limit as b goes to infinity, integral from 3 to b, so that lower boundary is going to be 3 there, so k equals 3 to infinity, of 2 over x squared plus 1 dx. So I like that they threw this in here because this reviews one of those strange patterns that we had looked at that you just kind of have to memorize. This is your arctangent pattern. So u equals just plain x, a equals 1. And so this is going to be limit as b goes to infinity of 2, because we have a 2 here. This 2 could have been outside of the integral as well, but we're going to have 2 as a coefficient, 2 arctangent of x. It would be x over 1. And also there would be a 1 over a out front, but that would just be 1 over 1. So I kind of ignored that because a was just 1. Right? Such that from 3 to b. And so we're going to do upper boundary minus lower boundary. So that would be 2 arctangent of b minus 2 arctangent of 3. Now, I don't know what arctangent of 3 is, but I know it's some number. And if I were going to type this in the calculator, I could get some decimal for that. I don't know what it is off the top of my head, but I know that it's some value. And then lastly, we're going to do this limit to infinity. So let me draw a picture of tangent here. So here's pi over 2, negative pi over 2. Tangent is going to go through the origin and have asymptotes right there. And you get this wiggly looking thing. And then you would have like an infinite number of these. That's your graph of tangent. So if we're doing arctangent, we're doing this backwards. As we go to infinity, it's going to give us pi over 2. So this would be 2 arctangent of pi over 2 minus 2 arctangent of 3. So I do not know what all of this is just off the top of my head. Or no, I'm sorry. I wrote the arctangent in there again. Again, I'm sorry. Arctangent to infinity just is pi over 2. I don't need the arctangent in there anymore. I'm sorry. I evaluated that part. So I'm sorry, it's just 2 times pi over 2. This whole thing with b going to infinity just is pi over 2. All right, so 2 times pi over 2, that would actually just be pi minus 2 arctangent of 3. So again, I don't know exactly what that is, but I know it's just a number. I know it's just a value. And so this integral converges. And so what that means is that the series also converges. So since we got just a value. Now, if it had gone to infinity, then it would diverge, and so the series would also diverge. Whatever one does, the other also does. That's what your integral test does. All right, so that first one converges. Terminal 2, I promise these other two won't be as bad as that one. All right, this one is geometric, and r is 6/7. If you want to put like a 1 in here, it's 1 times 6/7 to the k power. And so that's going to converge. So for geometric, if r is smaller than 1, 6/7 is smaller than 1, then it's going to converge. If it's bigger than 1, then it's going to diverge. All right, and then the third one, this is an alternating series because of that -1 to the k power. So we're going to do our alternating series test. Limit as k goes to infinity of 1 over k, and that's going to go to 0. And then 1 over k plus 1 is going to be smaller than 1 over k. That is true. This is going to have a bigger denominator than this one, so it is the smaller fraction. And so that also converges by the alternating series test. So this one, you have to know a lot of stuff just to answer this one question. This one was your integral test. Since this came out to just a value, that series converges. This one was geometric. R is smaller than 1, so that converges. And then this one was the alternating series test, which we found both of those things were true, so converges. So then answering the question on top of all that, it says, which of the following series diverge? Well, none of them. We got that they all converge. So that one is A, which is an awful lot of work just for one multiple choice question. All right, this number 3, I made this a bonus question. First of all, because this question is just really, really strange. And also there's like one step here where you kind of need what I'm going to teach you today. So I made this one extra credit. So if you got it, you got an extra 3%. If you missed it, then it didn't count at all. All right. So it says, which of the following statements are true? All right, Roman numeral 1. The series converges because the terms alternate and the limit as n goes to infinity goes to 0. We can't use that one because they left out the third thing. The terms alternate, this limit goes to 0, and a sub n plus 1 has to be smaller than a sub n. They left out the third condition there, right? So that one's not going to be true. And then 2 and 3 are pretty much the opposite of each other. It says the series diverges because this isn't true. And this says it converges even though that's not true. So basically just need to see whether the series converges or diverges. And I would do kind of the same thing they did here, is separate it into 2 different series. I don't like how they wrote this first one though. I think this looks really complicated. I'm going to kind of write it a little bit simpler. I'm going to separate it into 2 different series. So let's look at every other term. Here we have 1 plus a half plus a fourth plus an eighth, so on and so forth. Here, let me just go ahead and write that out. So that is geometric, and r is a half. So let me throw a question at you guys. Since r is a half, and just by typing in the chat, does that mean that this is going to converge or diverge if r is 1/2? Good, nice, that's going to converge. If r is smaller than 1, so that is going to converge. All right, and then I'm going to look at all the other terms, the ones that I didn't pull out here. So -1/9, and then what is it, negative 1/25th, and then negative 1/49th, and negative 1/81st, minus, so on and so forth. If you look at the format that they gave you for this, it's -1 over n+1 squared. You can compare that to a p series where p is 2, since you have that squared there. And that's more what we're going to talk about today, which again is why I made this one extra credit. But p would be 2 for that, and if p is bigger than 1, it's going to converge. So what we did is we separated it into 2 separate series, and both of them converge, which means if you put them together, it's also going to converge. So this one converges, so it is Roman numeral 3. So like I was saying, it can still converge even if the terms aren't decreasing. You just can't use the alternating series test to prove it. We kind of went a different method and broke it into 2 separate series. One was geometric and one you can compare to a p series. That question was just really hard. All right, well, they're all really hard. It's Calc VC. All right, number 4, which of the following statements about this series where a sub n equals this, which of the following are true? So Roman numeral 1, the series is alternating. Well, we have this -1 to the n there, so that's going to be true. All right, a sub n plus 1 is smaller than a sub n. That means that the terms are getting smaller. It means that they are decreasing. What I would do is just write out a few of them. We're starting at n being 2. So let's plug in 2 for n. All right, that's going to make this numerator 1. Well, actually, I'm going to sort of ignore that part because they had absolute values here. So I'm going to turn them all positive. So that would be 1 over square root of 2 plus 1. All right, comma. Now the next one would be 1 over square root of 3. Now this would be -1 because -1 to the third would be negative. And then the next one would be 1 over square root of 4 plus 1, and so on and so forth. We need to see if these are decreasing. I'm basically just going to compare the first two. Now without a calculator, square root of 2 and square root of 3 are awfully close to each other. They're both decimals, but they're very, very close. So if I take this one and add 1, and I take this one and subtract 1, this denominator is going to be larger than this denominator because these numbers are very close. So if I add 1 to this and subtract 1 from this denominator is bigger than this denominator, which means that this fraction is smaller than this one. So they're not decreasing. So this is not true. And then the last one, limit as n goes to infinity is going to be 0. Well, yes, if you plug in an enormous number for n right here, that's going to make the denominator infinitely large. So you end up with, like 1 gazillionth, which is really awfully close to 0. So that's going to be true. All right, so that was 1 and 3, so D for that one. All right, and then the last one, the alternating series test can be used to show convergence for which of the following alternating series? So the limit as n goes to infinity, that has to go to 0, and the terms have to decrease. They have to keep getting smaller. Well, looking at this first one, these terms don't decrease. We have 4, and then a 9th, and then it's back up to 1, and then an 81st, and then back up to a 4th. So that one is just all over the place. That's not going to converge. Here, these are getting smaller. We have 1, a half, a third, a fourth, a fifth, so on and so forth. Those are going to keep getting smaller. And if we do limit as n goes to infinity for this denominator is going to get infinitely large. So that limit will go to 0. So this one, yes. And then this last one, 2/3, 3/5, 4/7, the fractions are getting smaller and smaller, so that's good. But if we do the limit as n goes to infinity for this, let me write that out so it's a little bit bigger. We have 1n in the numerator and 2n in the denominator. And so you would use the coefficients, which would give you 1/2. And so that limit does not go to 0. So we cannot say that that one converges either for the alternating series test. So just Roman numeral 2, and so that one is B.